All right, so we're going to do this final exam from spring 2022. The problems here, they ended up being worth, these numbers that so this is what you could have done. So you could have gotten a 94. And actually, if you guys look through this and you're kind of like, wait a second, this doesn't match what I got, or whatever, what got entered into the spreadsheet. Just to cover any potential grading errors, I added 4 right here, so that really you could have gotten a 98 out of 94. So, this is kind of standard for me usually, is I like to give close to half of a grade. So this is, 4 out of 94, so that's, I don't remember, like 4.3% or something. So it's, it's not half of a letter grade, which would be 5 points out of 100, but it's pretty close. So it basically means that if I graded you accidentally a little harsher than I should have, it's okay. That doesn't mean, by all means, if you find an error, if you're looking through it and you found an error, let's talk about it. If I graded you incorrectly by more than 4 points, I will correct that. This is, for all, really, it's so that you don't really, hopefully it means you're comfortable saying, you know what, okay, this is the grade I got. Obviously, if I made a huge error, I forgot to carry a 1 or something, and I'm off by 10, well, then by all means, let's fix that. So that's there for you. Okay. I always wanted to be the cool teacher who had a who had a comic, so there's my far side. Anyway. All right, so let's go down here for the beam and loading shown. Oh wait, hold on. Let's talk about how we did on this exam. Okay, so these are most of the grades. This is, after the little curve to cover my grading errors. So these are most of the grades. And this is a stem and leaf diagram for those of you guys who don't know how this works. I said this is most of my grades. There were a few that were off the chart down here. So the way this works is, this person got 102, this person got 103. Then I had someone who got a 90, a 90, 2 90s, 191, 193, 194. There were nobody in the upper 90s, which was kind of interesting. There was an 87, an 88, an 88, an 88, an 89, and another 89. Okay, so hopefully that kind of tells you how this works. So this is the stem, and these, I guess, are the leaves. Okay, so this is called a stem and leaf diagram. And it's a way to show somebody all of your data. It's basically a histogram. Anyway, so you can see that, as a class we did, fairly well. The bulk of us were kind of in here, which is pretty good. The average, I had to drop the people that just didn't show up. There were a few that got zeros because they didn't take the exam. So if I dropped them, the average was a 78. But for the most part, the average was dragged down by some outliers up here. There were more people above that 78. On the whole, I was pretty pleased with this. I guess I don't remember what the median is. Oh, the median of those who took it was an 82. So somewhere between, somewhere in here, 82. Okay, which is awfully good. I mean, that's a B, so we have to be, well, I guess we don't have to, but as an instructor, I'm very happy if my average or my median or any of that stuff can get kind of in that range. Anyway, so that's how we did on this one. So either it was easy, or you guys studied well, or I graded easy. I tend to think that this is you guys doing well, not to do with me. I try to be consistent, and some of you guys just really came prepared. It was awesome. So good job on that. Anyway, so let's go down here and let's talk about this one. For the beam and loading shown, draw the shear and bending moment diagrams and label all important values on the graphs, 10 points each. Determine the magnitude and location of the maximum value of the shear and bending moment. Okay, so the first thing we got to do here is, I'll find my little ruler. I think I had it. Okay, I know I got it out. Okay, so we need to figure out reactions first, right? So almost nobody did this. And in fact, I don't even usually do this for these problems. But, a little free body diagram never hurts, okay? And the goal of this, of course, is to determine the reactions, right? So we've got this force down here. This is 12 kips. I've got a moment right here of 75 foot kips. And then I've got this downward force, which, you know what, I don't even want to deal with that downward force, right? Because it's not really, you know, as far as the global free body diagram, that's not really what's going on. What's really going on is I've got 2 kips per foot over, well, not what's really going on, but how I'm going to represent it on this graph is I've got 2 kips per foot over 6 feet, so that's 12 kips total. And in the global sense, it's 12 kips acting at the centroid. So this is 3 feet and 3 feet of that rectangle, right? Okay, and then we've got another 4 feet over here. Okay, let's draw that 4 feet. Now the last thing, of course, is, well, we're going to get rid of this wall here. Okay, and as soon as we get rid of that wall, there's just a point over here, which I said was A. I think one person in the class did not decided that was not A, but that's okay. I figured it out. Anyway, so at A, by getting rid of that wall, I've gotten rid of its effect here. So it has an effect of AX, AY, AY, and then a moment. And we like to draw those moments counterclockwise. So we'll call that moment at A. Okay, so now we should be able to solve this. And a lot of us really struggled with the moment equation here. I'm not sure what's going on there. I highly recommend that we study that prior to, I don't know, dynamics. Dynamics is harder than this class, so just be aware of that. Yeah, I mean, there's just no way around it. It's harder. Okay, so here we go, and we'll go, okay, let's see. Sum of the forces in the X is pretty easy because there is only one, and that's AX. So AX equals 0. Cool. All right, trivial. All right, sum of the forces in the Y, that's not really going to be very helpful because there are, well, actually, no, it will be, all right? So the one nice thing about these cantilever problems is that you can solve all the equations just kind of like right off the bat. So we've got an AY going up. We've got minus 12K going down, so that's this one. And that, I wrote 12 feet, but that's a 12K, isn't it? 12K. Okay, minus 12K equals 0, so AY equals 24 kips. Okay. So now we need to do the moments, and we'll do, okay, the sum of the moments, and yeah, I'm going to do them at A equals 0. So we're going to expand this, and we're going to start with MA, which is positive. Okay, so that's this one. And then we need to get this 12, which is going that way, so that's a negative 12 kips times 3 feet. Okay, now we got the 75 right here. Okay, so that's also a negative 75 foot kips. And now we need to deal with this 12, which is causing that. So minus 12 kips times 10 feet equals 0. Okay, so that's all of my forces and moments. And if we do the math on this, I think we're going to get 231 foot kips. Let's see here. So yeah, 231 foot kips. Okay, so we're good. So now we're going to go back over here, and we're going to look at the global thing here. I'm going to pause it for a second while I draw these vertical lines. Okay, so we've got the vertical lines, and now we're going to draw the forces that are acting here. So I've got a 24 kips here, and I've got, what, 231 who are going this way. Okay, 231 foot kips. Not my best drawing of a moment, but, you know, what do you do? Okay, so then I've drawn the vertical lines anywhere where things change, where something interesting could happen, etc., etc. And so, well, my ruler slipped. Anyway, so this is my shear in kips. Okay, and by putting kips there, I don't need to write, you know, the units as I move through. Okay, so now I'm going to do the area here. And so we'll kind of do the, not area, A. A is where we start. So I'm going to start from A. I'm going to work to the right. And I'm just going to do everything that this thing tells me to do. So the first thing I'm going to do is it tells me to go up 24 kips. So I'm going to go up 24 kips. So I'll use each square to be 5. So that's going to be about right there. So I'm going to put a number 24 right there. Obviously, my lines are not super great, right? Anyway, so we get up to 24. And then I'm going to go down 2 kips per foot. for 6 feet, so I'm going to go down 12. So I'm going to end up over here. After I've gone those 6 feet, I'm going to end up at 24. And I will have gone down a very steady 2 kips per foot, so that's going to be a straight line. Okay, here we go, like right, like that. Okay, not a perfect line, but whatever. Okay, so now we'll notice in here, nothing happens. Okay, so we're going to stay at 12 all the way across. Okay, until we get here, and then we've got another force, and we're going to go down 12 to right here. Okay, so that's what we should have gotten. Okay, and now it's customary to shade that in. I don't want to shade it in just yet. I want to find the areas of these things because we know we're going to need those for the moment diagrams. And so the area of this rectangle is 12 by 4, so this is going to be 48 foot kips. Okay, notice it's positive. And then over here, I guess I could put a little positive on there. Then over here, this is a trapezoid. And so what I like to do is I like to do the average of these two, which is 18. And then I'm going to multiply that by 6. 18 times 6 is 108. Okay, and a lot of you just broke it into a rectangle and a triangle, and that's fine too. However you like to get that area. Okay, so then we're going to go, it's customary to shade it in. I have no idea why. It does look nice, admittedly. Okay, so now we're going to move on. I guess I don't really need A on here, right? That's a little kind of out of place. So I guess what I'm going to do is I'm going to move on and I'm going to draw, well, I need to extend these lines. All right, so we're going to do, this is going to be the moment diagram, and it's going to be in foot kips. Again, we're not going to stress, I don't know, we're not going to worry about writing the units all over the place in this thing. So we're going to start by, we're just going to kind of do what it tells us again. So basically we've got everything that's in this drawing diagram, and then we've got these 2 moments that we need to account for. Okay, now what I want to remember is that on, this is, this 231 is a counter, so normally we call that a positive 231. And this 75 is a clockwise, so normally we call that a negative. However, on our diagram, they go the opposite direction. Okay, so that's just something to be aware of. So this is going to be a negative, and this is going to be a positive. Okay, so let's go here. And where is my little trusty dusty ruler? So we're going to start by going down 231. Okay, so I'm going to have to make a decision where that 231 is. So let's call that, I don't know, 100, 231. So we'll go to right about, that's a little high. Anyway, 231. Okay. So then what we're going to do is we're going to add 108 to that. So 231 plus 108 is 123. So that's, I don't know, like right in here maybe. So 123. I didn't like the handwriting there, 231. Okay. And then, well, let's just get all of our points, right? So then we're going to go up 75. So we're going to go right up to about right there. So if I go up 75, I'm now at 48, right? And then I'm going to keep going to the right, and I'm going to add this 48. Okay, and that's going to get me right back to 0. Okay? So then the question is, well, how did we get from one point to another? And what I want to remember is that the value here is the slope here. Okay, so notice these values are positive but decreasing. Okay, so the slopes here should be positive but decreasing. Right, so positive but decreasing means it's going to have a shape like that. Okay, for the slopes. Okay, now I'm going to erase that because that's not going to get me to my point that I want. Okay, right, but it's not going to get me to 123. So here, let's use a pencil here. 123, if it was a straight line, it would be something like this. Right, but I need to draw a concave line. Right, so I'm going to do that to the best of my ability. Notice it's still positive here, so that's also kind of the hard part here. You know, my artistic abilities are not supreme here, right? But something along those lines. Okay, so notice it's concave. It's concave down. It's still positive. The slope is still positive at that point. You know, I'm just not a perfect artist. And I didn't really expect you to be either. Okay. So anyway, so we go, you know, this is a jump there. And then what we're going to do is right over here, we notice the positive, you know, we've got a, you know, we need to know the value here because it's the slope down here. Okay. So notice that we've got a positive slope, a positive value, and it's the same through that entire section. So in other words, we've got a positive slope, and it's the same, or it's constant slope. Okay, so we're going to go like this. Okay, and that's it. And then we're just going to go because it's customary. Okay, so how did I grade you guys on, well, this section, we'll talk in a second about the other thing, is it was values in shape, right? So if I put all these points right here, 1, 2, 3, 4, 5, 6, each of those points is +1. And then the shape, did you go up right here? That was 1. Did you go here? That was 1. Did you not do anything right here? That's a +1. Did you go flat here? That was a +1. Did you go here? It's a +1. Okay. And of course, this could get a little challenging if somebody got these, you know, like if you got the first number off, and that's going to kind of shift your whole diagram up or down. So we just do the best we can. Sometimes, you know, it's a little bit, you know, you may have gotten this value off, and then that kind of affected you more than once, because it is an important thing to notice is that V equals 0 at the ends. Okay. And it has to be, because everything has to add up to 0. Sum of forces equals 0. There's no internal forces there. Okay, so to, you know, clean everything up. Okay, same thing will happen here with M. M must equal 0 at the ends. Okay, notice that that happens on both ends. Okay, and that's what this moment right here is all about. That's the external moment to bring it back to 0. So we did the same thing over here. So, you know, +1 for all of these dots, okay? And then +1 for the shapes, okay? So this is +1, +1, +1, +1. And then this one gets an interesting +2 because you end up with, you know, well, because you get... it's kind of like combining this shape right here with that extra point. Looks like I accidentally gave you all an extra point there. Okay, well, Merry Christmas. Because those add up to too many points. All right, well, anyway, so it was supposed to be 10 and 10, but it looks like it might have been 10 and 11. I guess the people who would have lost out would have been the people who did it 100% correctly, because I didn't add up the points exactly. But so if you made an error on this, you probably got an extra point if you closed that right in there. Okay, anyway, so the maximum shear is blank and located blank distance from A. So the correct answers here, based on my diagram, the maximum shear is 24 kips and is located 0 feet from A. And then the maximum moment is right here, is 231 foot kips, and it is located 0 feet from A. You know, and these blanks are worth, you know, +2, +2, +2, +2 for, you know, another 8 here, so 28 on this page. I will note that, you know, these answers down here are based on your diagram, okay? So if you made mistakes up here, you know, you still should have been able to get this, okay? And for the most part, you guys did. So that's how we do this one. So let's move down to this one. Okay, determine the location of the centroid of the region shown below. Okay, a few of you tried to do this one by splitting it, by doing horizontal boxes. That's a big, ugly mess. One of you got actually pretty close. I can't remember. Well, of course, really had no idea who it was because I grade blindly. I should probably go back through the pile and find it, but it was pretty interesting. Somebody got pretty close. But a vertical box is, here's the problem with the horizontal box. This section is defined as going from 2 to 1. And this section right here is defined as going from 2 to x. Okay, so in other words, you have to split this up into two sections, with this being one section and this being another section. And then you would have to treat this kind of like a chart, where we do it by composite shape. And I could show you how to do that, and maybe this would be the place. I don't know. I'm not doing that right now. Maybe I'll come back at the end of this exercise. Anyway, let's solve it with vertical boxes first. Okay, so here's a vertical box. Okay, now it's got this point right here is the point x comma y. Let's zoom in. No reason for that, right? And so what that means is, if I use a trusty dusty pencil, that means this distance right here is x, and this distance right here, if I go right through the middle of this, is y. Okay, and then that little box that I just drew, so here we are right here. That little box right there, it's got a width of dx, okay, and it's got a height of y. Now, we need to find the location, if you will, of the centroid. So the centroid is right here, okay? So if that total distance is y, that is y over 2 from the bottom, right? Okay, because there's just as much above it as below it. And then its distance from the, its x-coordinate is like right here. That's an x, right? And so that's, it's the exact same as the one above it, right? So so this x and that, whatever that one is, this one is, right? So it's x. Okay, so that's cool. So now we should be able to start working our equation. So our equation looks like this, right? So it's x bar equals the integral of x tilde, no, not a comma. There's no commas in the middle of math equations. dA over the integral of dA. And the y bar equals y tilde dA over the integral dA. Okay. So I think, this the denominator of both of these is exactly the same. So I'm going to go ahead and do that on the side. A lot of you, for some unknown reason, solved that twice. A and B did it differently and got different numbers. I don't, do that the easiest way possible. So I'm going to go ahead and get my dA. I'm going to do it over here just because it can make my life a lot easier. Okay, so the integral dA. Well, what is that? Well, that's just the area of this thing. Okay, so we're going to integrate this thing. And my dA is just the area of this little element. So it's the length times the width. So it's y times dx. Okay? And we're going to stack these boxes up from x equals 1 to x equals 2. So we're going to go from 2 to 1. Okay? So the big problem I have right now is y and dx. So I'm going to turn that y into an x by using this formula right here. Okay, so I'm going to go x squared dx from 2 to 1. Okay, and I'm going to start working down, which is what I should have been doing from the beginning, right? And so we're going to integrate that x squared. I'm going to get x cubed 1/3 from 2 to 1. Okay, so if I plug that in, I get, what's that? 8/3 minus 1/3. Well, really, I get 1/3 of 8 minus 1, right? So a equals 7/3. Okay, and that's how this is done. Yeah. Okay, so that's the denominator of both of these things over here. So 7/3. And I'll probably just start writing that as the area, because that's kind of an easier way to do this. Okay, so then for the x thing here, for this guy, then I've got x equals Got the integral of x tilde. Well, what's x tilde? Well, that's this thing right here. That's x times the dA. Now, we've already done the dA right here. This is the dA, and this is also the dA. I'm going to use it here because I know that that's going to be the easier way to do it. So I'm going to put in x squared dx. X squared dx. Okay, all over the dA, which, the integral of dA, which I'm just going to write it as a for now because I don't really feel like writing out 7/3. But, you know, we'll get there. Okay, so x bar equals the integral from 2 to 1 of x cubed dx over a. So x bar equals x to the 4th. That's supposed to be a 1/4. I don't know what I was doing there. 1/4 from 2 to 1. All over. Now is probably a good time to start thinking about this a. So I'll go ahead and put the 7/3 in there. And we'll say x bar equals, what's that? 1/4 of 16 minus 1. So that's going to be 15 over 4 divided by 7 over 3. So x bar equals, this is 45 over 28. Okay. That's a pretty annoying number, right? I mean, technically, you know, we should also remember, by the way, that this is inches squared and this is inches cubed. So now we're left with inches. Yeah, usually when integrating, it can be a little bit cumbersome to keep track of the units. I'm not saying you can't do it. What you need to remember is that this is 2 inches to 1 inch, 2 inches to 1 inch, and then it will kind of all, or well, it should all pop out nice for you. And it actually doesn't pop out so nice on this one, does it? And there's a reason for that. It's because why? Well, it's just some weirdness here. If you notice this equation does not work units-wise. So when you have a y equals x squared, there needs to be units-wise. So if I plug in an inch here for x, I get inches squared for y, but clearly y is supposed to be, you know, in inches. So there's actually an imaginary 1/inch right here, which probably most of you guys don't want to think about. So if that confuses you, don't think about it. Do what you probably did, which is you probably got to the end and you just wrote the word inch on the end, which is totally fine, at least in this case. Anyway, so, okay. So let's do the other side. Let's do the y bar. And again, you know, we're just going to leave that area on the bottom alone until we get, you know, where we're going. So it's frozen on me, as it likes to do. Okay, it unfroze. All right, so we're going to go y bar equals integral. So I need the y tilde, which is this y over 2. So y over 2. And then the dA, I'm going to actually write it as y dx here. Just because I already have the y's there, so I might as well just do that. Okay, and then I'm going to leave that as a on the bottom. Oh, no, don't do that. Okay, so, all right, so again, you know, I've kind of got that same problem I had earlier, which is I've got y's, but I've got a dx. So to solve this, I need to do y bar equals, here's my area on the bottom. That becomes y squared, but remember y equals x squared. So y squared equals x to the 4th, right? So I'm going to have 1/2, and then that y squared is becoming x to the 4th dx. Okay, so y bar equals, okay, 1/2, and then we're going to take that x to the 4th, I'm going to make it x to the 5th, 1/5 d, and no, there's no more dx's. A lot of you guys struggled with this. You wrote all kinds of weird stuff. I think you need to go back and look at integration and kind of think about what these things mean. A lot of times you guys kept writing the dx, or you never wrote the dx. It's kind of important. Anyway, so we've got a 7/3 on the bottom. Okay, so if we solve this, we end up with, let's see here. So it's going to be 1/10 times, I'm going to plug that 2 in, and I'm going to get 32. Plug that 1 in, I'm going to get 1. I'm going to divide by 7/3, and I'm going to get y bar equals 31/10 over 7/3, which if you do the math there, I think it's 93 over 70 inches. Okay, horrific number. And then, of course, you'd plug those into your calculator if you wanted to get this in decimals, and you would have said 1.61 inches, comma, 1.33 inches. Okay, so we're going to go over here, and let's talk about how did I grade this. And let's see, I kind of did the area as its own thing, and basically getting, this formula right here was worth 2. And then integrating correctly was worth 1. I guess it was integrating correctly was worth 1, and then getting these limits was worth 1. Okay, and then obviously if you had an algebra error or something like that, it took off on that on top of it. Okay, so then we did the same thing over here. I mean, it's basically the same thing, except these are a little bit more complicated, so they're worth a little bit more points. So this is worth +3, integration +1, the limits +1. Okay, same thing over here, kind of getting this set up, +3, +1, and the limits are +1. And then just kind of knowing what to do with that, right? Because I did these piecemeal, right? I did them over here and then over here. So then as long as you knew that ultimately you were going to divide them, and if you divided them correctly, then that was worth 3 here and 3 there for a grand total of 20 points. Okay, so that's how I graded that one. A lot of you guys have some kind of minor issues with integration. So it just might be something worth kind of paying attention to and trying to correct as you get forward. Just kind of be a little strict on yourself about the dx's and the dy's, and always thinking about what the limits of your integration are and things like that. It's nothing that you can't fix. It's not like you need to retake calculus or anything, but it would be very helpful to just kind of be thoughtful about it and try to, pay attention to it when you've got to integrate. Okay. That's not what I wanted. Anyway. Okay, so number 3. This one's worth 16 points. Locate the centroid of the cross-section X bar and determine the moment of inertia of the section about the centroidal y-axis. Okay, so people broke this thing down into different ways, and I forgot that one of the things that I would like to do here is, tell you guys which shapes to do, because, that makes my life easier for grading. I'm going to go ahead and do shape 1, shape 2, and this negative shape here. Only one person successfully did a negative shape with this triangle right here. Like somebody did this, did a negative shape right here, or a fair number of you did a negative shape with this triangle, but only one person ended up getting it correct. So I'm going to go ahead and include that in my calculations. I'm not actually going to do that one. Really we only want to do 1, 2, and 3, but I will go ahead and create another, another row for number 4, so that if you did it that way, you can kind of see what it is that we did. Okay, so, or what should be done. Okay, so I'm going to start over here by doing shapes. Okay, and so we'll do this shape, and the circle. Okay, and down here, just if you wanted to have done it this way, I'm gonna include shape number 4, which I guess should be drawn like this, right? Sorry, my dogs are playing and barking. So, all right, so the first thing we need for each of these shapes is we need x tilde, we need an area, and we need an x tilde a, right? Because the equation for the centroid is x bar equals x tilde a, summation, or the summation of the a's, right? So, so we'll start with shape 1. Maybe I should number these 1, 2, 3, and this is the 4 down here. Okay, so the x tilde for shape 1 is somewhere over here. It's closer to the flat side, right? And if you look it up, it's going to be that it's going to be 1/3 of that length. So, you know, this length is 12, so it's going to be 1/3 of that, so it's going to be 4. This is in inches. This will be inches squared, and this will be inches cubed, right? And remember, it's always closer to the flat side. Okay. Note that for shape 4, which is the flat side is over here, so its location is going to be at 8. Okay. Shape 2 is this this big rectangle, and so it's got a height of 6, and I'm sorry, it's got this side is 12, so its distance from over here is going to be like a 6. And then for the circle, so you know it's about what, I guess it's exactly right here. And then for the circle, the center of the circle is right there, so it's at a location x equals 4. Okay, now we need to get the areas of these things. And areas of both triangle 1 and triangle 4 is 1/2 the base times the height. It doesn't matter what you call the base and what you call the height here. Either way, it's 12 times 1 divided by 2, so it's going to be 6. 6 and 6. For our rectangle, it's 6 times 12, so that's going to be 72. And for our circle, it's pi r squared, where the radius is 2, so that's going to be 4 pi. Or we could make it 12.566, and this is where we have to start being careful about, this is negative space, right? Same with this one, if we used that one, okay? The x tilde a is here, and so that's going to be 24, 432, and negative 50.5.2, dadgummit, 264, okay? And for this one, it would be negative 48. Okay, if we had done that. All right. So to get me my sigma here, or my sorry, I need to sum some things, right? So we would sum this and get 65.434 inches squared, and to sum this we get 405.74 inches cubed. Okay, so up here for my x bar, I would get 405.74 inches cubed divided by 65.434. So x bar equals 6.2008 inches. Okay, an awful lot of sig figs. Okay, so sometimes I'll actually put this in this chart, and just every one of them will share kind of the global centroid, but I'm not going to do that right now. All right, so the next thing we want to do is I'm going to do x bar minus x tilde, right? The distance between these centroids, right? The d, okay? So this is d equals, okay? And so what I'm looking for is, you know, the global centroid's right here. So x equals x bar is like right here. So what I want to know is how far is that to each of these centroids, right? That's my D. Okay. So in this case, it's, you know, so for this first one, it's 4 compared to 6.2008. So they are 2.2008 apart. For the second one, where is that one? That one's at 6, right? So 6 to 6.2008 is 0.2008 apart. And for the last one, it's 4. So distance from 4 to 6.2008 is 2.2008. Okay, and then this last little, this little sliver right here, it's 8 minus 6.2008. Okay, so anyway. Yeah, so then I guess the next column I need is AD squared, or AD squared, right? So I'm going to square this column, and I'm going to multiply times that column, okay? And I'm just going to go ahead and fill that out. 29.060, this is in inches to the fourth. 2.9031, and negative 59.7 398. Okay, so I know that I'm going to need to add all those up, so I'm going to go ahead and add them now. Negative 27.435. Okay. Let's see here. Yeah. All right, so then we need I, and this is important. This is IYC, okay? Because what we're looking for is we're going to be bending it around this thing right here, okay? So that is an axis y prime, okay, or something like that, or IYY. So like over here, I'm looking for IYY. So I need to look up the IYC. So this is the moment of inertia if I bent these things around their own local centroid, okay? And so a lot of you got these formulas wrong, and I would suggest very strongly that you go back and you look them up. If you look up there, there's going to be two IYs. So one is an IYC, and the others are no IYY. So this one is if you bend it around the y-axis. Okay, this one is if you bend around the centroid. Okay, now this is both of these are local off that chart. Okay, they have no idea where this problem is. They have no idea what the global is. Okay, so I don't even know why they put this on there. I don't know when you will use that. There might be a time. Okay, certainly in this class you don't use it. You know, I'm not the expert here. You know, because you know I'm not a structural engineer, but so maybe that will come up at some point in time. But for this top sliver of a triangle, it's going to be 1/12 the base of that triangle, which is 1 inch, times the height of that triangle, which is 12 inches cubed. Okay? Sorry, it's not 1/12. If you look up on the chart, you will see that it's 1/36. Okay? And the same thing is going to go for this one down here, 1/36 times 1 times 12 cubed. Okay? In either case, it's going to end up being 48. And 48. You can hear my little monkey in the back. She's very vocal. By monkey, I mean dog, by the way. Okay, for the rectangle, it's going to be 1/12 the base, which is going to be 6, times the height, which is going to be 12 cubed. Okay, and if you do that math, it's 864. And this one's negative. And then for the circle, if you look it up, it's pi r to the 4th over 4. Okay, and if r is 2, then you end up with a familiar number. It just kind of works out that way. Okay, that's just a coincidence in this case. Okay, and if we add all those up, we get 899.434. Okay, so the IYY equals the summation for all the shapes IYC plus AD squared. Okay, and that's the sum of this and that. So the IYY equals 872.00 inches to the 4th. Okay, and that's pretty cool. And then we've got this number right here. So we go down here and we say 6.20 inches and 872 inches to the 4th. Okay, this is actually the grading. This one I wouldn't say I like grading this one because I don't like grading anything. But it's a very easy grade. Basically, I was looking at the rows that you had to figure out. So +1, +1, +1, +1, +1, +1. Over here, +1, +1, +1. And over here, +1, +1, +1. Okay, so that's 12 for 12 points on here. Okay, and then obviously you have to know what to do. Obviously, you have to know what to do with those numbers. So there was another 2 points in actually figuring out your x-bar and 2 points here. Now, obviously, this depends on these numbers. So if you make a mistake somewhere in here, like let's say you only got 11 points here, well, that's going to screw up these numbers. So I have to actually calculate these for you. Like if you made a mistake, like instead of saying 72, you accidentally got 64. Well, that's going to screw up everything. And so I just had to recalculate those to see if your other answers were correct. And that's just how it goes. That's, that's the joy of grading. Anyway, so it all comes out to 16 points. Okay, so let's go on down to this. Determine the force in each member of the truss shown below. The biggest problem we had here was with reactions. Some of you guys did a really wonderful job of going, you know what, I don't know how to get the reactions, or I'm gonna screw this up, but I don't care, I'm just gonna keep working, which is, I mean, obviously it's not ideal, like if you were on a real job site or something, you wouldn't want to do that. But on a test, yes, keep working. Just use a variable or something. One of you emailed me and couldn't find the angle and didn't know how to do it with an angle, so they just had a theta running through the whole thing. And that was totally fine. I took off 2 points for not knowing theta, but 2 out of 30, like who cares, right? I mean, I'm not saying we don't want those points. We always want those points. But yeah, so just, like keep working, right? You get stuck, it's okay. All right, and so let's start by talking about why global equilibrium was confusing for some of you guys. And that's because if we look at this, the first thing we'll note is that we've got pins at A and E. So our first thought is to do this. Okay, AY, EY. Okay, EX and AX. So the problem here is there's 4 unknowns and only 3 equations. So you're not going to be able to solve that unless you know something else. And it's actually true in this case. You could probably have started doing this problem by joints. Started over here on this joint and just worked your way through, and you would have ultimately gotten the external forces. But I'm not really going to concern myself too much about that, because the easier thing to notice is down here at E, is to notice that this force, whatever it might be, is going to be, ED is a 2-force member. So we can expect this force to either go like this, go one way or the other, right? So I don't know which way. Actually, I do know which way, because it's definitely going to be pushing, because if we look at all this, it's trying to make it go this way, so this is going to have to make it go the other way, right? So based on that, I'm going to go ahead and solve this. But it was just something that you had to notice, and I'd say most of you got that, but it did throw a loop for some of you, and I was very pleased with how you guys handled it. If you couldn't get it, you just said, you know what, I'm just going to keep working, and I'm going to assume that my AY is 0, because I don't know what AY is, or something along those lines. Okay, so we're going to call this E, okay, and it's going to be on an angle here. Now we have to figure out what that angle is, and we'll note that that angle is the same as this angle. So this is a 2, 3 square root of 13 triangle, right? Not so happy. So what we're going to do is we want to get that angle, theta. So because that theta is going to be the same as this angle theta, is the same as this angle theta, is the same as, this angle theta, right? So, right, it's the angle for this thing. So what I'm going to go ahead and do is I'm going to go ahead and do theta equals the inverse tangent of the opposite 2 over the adjacent 3. Okay, so theta equals 33.690 degrees. Okay, so that's a nice, horrible angle. Next time I do this, I'll give you a 30-degree angle or something. But then again, you guys won't be here. Thankfully, you guys will have moved on to brighter and greener pastures. Okay, so let's go ahead and I'm just going to erase that. Just come back to that if you need it. Okay, so what we're going to do now is we're going to start doing sum of forces in X, sum of forces in Y, sum of the moments. And the easiest thing for me, actually, right off the bat, is to go ahead and do the moments, and I'm going to do the moments at A. Okay, so the sum of the moments at A equals 0. Okay, so we're going to deal with this 3 kilonewtons. 3 kilonewtons. Okay, it's got a moment arm of 3 meters. Okay, and if this is positive, it's causing a negative moment. Okay, now I want to do this 2 kilonewtons. 2 kilonewtons. Okay, it's got a moment arm of 6 meters. Okay, and it's negative. And then I got to deal with E, right? And the problem with E, of course, is that some of E is going this way, and it's going to go right through there. And so we don't need EY. We do need EX, however. So EX is creating a moment. So EX, it's got a moment arm of 4 meters. And it's causing it to go that way. So we'll call that positive. Equals 0. Okay, so if we solve this, I get EX equals 5.25 kilonewtons. Okay, and we'll note that if I have EX, then I also have EY, and I also have right, because let's just go ahead and get E, right? E. So let's actually do the trig, right? Because we don't end up doing this trig nearly as often. But let's say the cosine of theta equals the hypotenuse E, the adjacent EX over the hypotenuse E, right? So we'll say the cosine of 33.690, that's my theta, equals 5.25 kilonewtons divided by E. So if I rearrange that and solve, I get E equals 6.3097 kilonewtons, right? And so if I do that number times the sine of theta, then I can get, let's go ahead and do that. Let's go ahead and do EY equals E sine of theta. So EY equals 6.3097 kilonewtons times the sine of 33.690 degrees. So EY equals 3.5 kilonewtons. Okay? And there were several ways that you could have ended up getting these numbers. But, it is what it is. Okay, so this E is going to be 6.3097 kilonewtons. And I'm going to keep the X and the Y just because it's going to make my life a little easier. 5.25 kilonewtons, 3.5 kilonewtons. Okay? Now what we're going to do, I'm actually going to erase all this moment stuff because I don't want to look at it right now. Okay, it's because I'm trying to stay close to the diagram here. So let's go ahead and we need to get AX and AY, so we'll do the sum of the forces in the X equals 0. And so I've got AX plus EX equals 0. So AX plus, what's EX? 5.25 kilonewtons equals 0. So AX equals negative 5.25 kilonewtons. Sweet. Okay, and then we'll do the sum of the forces in the Y equals 0. And I've got AY plus EY minus 3 kilonewtons minus 2 kilonewtons equals 0. So AY is what we're looking for. EY is 3.5 kilonewtons minus 5 kilonewtons equals 0. So AY equals 1.5 kilonewtons. Sweet. All right, so we get all that stuff. All right, so we're going to go over here, and I'm going to go ahead and put these on my diagram. Okay, I guess, all right, so now I've got everything on the diagram, and I think, well, I guess I don't have, erased theta. So let's go ahead and put theta back in there. And there's a theta right here, right? Okay, those are all my thetas. Okay, so what we're going to do now is we're just going to start working this thing. And I think I'm going to work without numbers and then come back in and put numbers in, maybe. I don't know. Yeah, so let's just go joint by joint. And you could have started this thing wherever you wanted. And you would have gotten, whatever you would have gotten. But so I'm going to start at A right here. this little A right here. So take a mental image of A, you know. And we're going to go over here and we're going to draw joint A. So joint A is going to be, you know, maybe I'll zoom way in. You know, I could zoom all the way in here and do joint A. Let's do joint A, and we'll make our equations really, 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 really tiny, right? So here's A. Okay. And at joint A, I've got two members doing this, like this, and like that. Okay, so I'm going to zoom way in. Okay, and then I've got, you know, AY. And I've got AX going this way. Okay, and then I've got these things pulling this way and this way. Now, they may not be pulling, but I'm assuming they're pulling. Okay, and these things are AB and AD. Okay, and I got those from the larger A to D, A to D, and A to B. Okay, so let's zoom way in. Okay, so now we have no mess to look at. Okay, and let's create an equation here. Okay, so in the x direction, sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. Okay, so the y direction is going to be easier, and it's going to be AY, because these are known, right? So AY minus AD, let's see, we need this is angle theta, so it's going to be the sine of theta equals 0. Okay, I'm going to go ahead and tell you this right now before I keep going. This equation is going to be worth 3 points. Okay. And that's before you plug in, right? Because what you're going to plug in is going to be based on your solutions, right? So if I plug in there, I'm going to get 1.50 kilonewtons minus AD, which is what we're looking for, times the sine of, in fact, these are given, right? Or known. This is 1.5 kilonewtons. And AX is, what was AX? Oh, 5.25 kilonewtons. Okay, and the reason this is the equation that matters is because because if you make a mistake getting you know, if you make a mistake prior to this, I don't want to take off the points for it, right? So as long as you get this equation, you're in good shape. Okay, so AD sine 33.690 degrees equals 0. So AD ultimately comes to 2.7042 kilonewtons. Okay, and that's going to be a trend with this problem, is that all the angles are going to have horrific numbers, and all the verticals or flats are going to have really pretty numbers. Okay, so be prepared for that, and that happens when you've got coordinates that are pretty in the x and the y and not on the diagonal. Okay, so anyway, some of the forces in the x direction we now need to do, and so we're going to have, let's see, we've got AX right here, so we've got negative AX. We're going to add AB, and then we're going to add AD cosine 33.690 degrees equals 0. Okay? Again, remember, this is the equation that's worth 3 points. Okay? So if we solve that, we're going to plug in negative 5.25 kilonewtons plus AB plus AD, which we found right here, 2.7042 kilonewtons times the cosine of 33.690 degrees equals 0. And so AB equals 3 kilonewtons. Okay, we'll note that in both of these cases, this one then is in tension because I assumed tension. This one is in tension because I assumed tension, and I got a positive number. Okay, so the last point for each of these is your interpretation of this. Okay, so if you drew an arrow like this and you got a positive sign, then you should have gotten tension. Okay, so that would be worth 1 point. Okay, if you had drawn this arrow this way, you would have gotten a negative number, and you would have still gotten tension, and it would have been worth 1 point. Right? So it's just, you know, it's, some of you got tensions and compressions that were correct, but they didn't match your work. It was like you were kind of just assigning tension and compression haphazardly. And so that's, you know, that's not acceptable. So anyway, oh, the other points, because there's going to end up being, well, I'll explain in a second. Well, yeah, so let me back up real quick. You're going to need 6 equations, because there are 6 unknowns that we're looking for in this thing. So there are 1, 2, 3, 4, 5 joints, 4 joints really. So there's really 4 joints that you could do these equations on. Okay? And so with each joint giving you 2 equations, that means you could end up with 8 equations. Okay? So what you need to do from a grading standpoint is I needed 6 equations, 6 out of those 8 that could solve for the 6 unknowns. Okay, and what that means is you've got 2 redundant equations, and you'll see as I go through it, I'm going to end up with 2 equations that are like not useful. There's just, you know, like they're, but they can be used. So these redundant equations can be used to check your answer. Okay, and so you don't have to do those, but you can, right? For each of these 6, it was +3 for the equation, and then +1 for the correct interpretation of tension versus compression. Okay, now you might say, well, that's only 24 points. The other 6 points came from 1 for each reaction. 1 for each reaction. So +2 for each reaction. Okay, and that's how the grading went. Okay, so anyway, so we've just done joint A. We've got to do joint B, joint C, and joint D, and that'll give us all 8 possible equations that you could have used to solve for this. Okay, so that was A, which I made it kind of small in there, and then let's go in and let's do B. Okay, and I'm going to do B right in here, right? Because I'm crazy like that. So I'm going to cut it here, here, and here. Okay, so we end up with something that looks like this. Okay, so I've got a force going downwards. I think it's 3 kilonewtons. Okay, and then I've got some other forces, and I'm going to go ahead and install those suckers. Right, so I've got, let's see, I've got AB going this way. AB. I've got, I think this is BC going this way. Yep. And I've got something going down here. Okay, or, you know, I would draw them all in tension. Some of you draw them in the way that you think they're going to go, and that's fine too. Okay, so now I'm going to zoom way in. And this one's actually pretty nice and easy, right? There's not really a whole lot of thinking to do with this one because, you know, the forces are, you know, so I know that negative AB plus, you know, there's no angles, and there's, you know, okay, so again, this is the one that's worth 3 points right here. Okay, so in this case, well, let me go ahead and get the y equation as well. Sum of the forces in the y equals 0. So I've got negative 3 kilonewtons minus BD equals 0. And again, this is the equation that's worth 3 points. Okay, now I'm going to go ahead and plug in there. Negative AB plus BC, where are we? So we're going to get negative 3 kilonewtons plus BC equals 0. So BC equals 3 kilonewtons, okay? And that, because I drew it in tension and I got a positive, that means it is in tension, okay? And then this one over here, we're going to end up with, let's see here. So I'm going to solve for this. I'm going to get BD equals negative 3 kilonewtons. And since I drew it in tension, and it turns out that it's a negative sign, so that means it's in compression, 3 kilonewtons compression, okay? And remember, this T or the C is worth 1 more point. Okay, so that's joint B. Okay, let's go to joint C. Okay, here's joint C, get a, kind of a look at it. Let's go ahead and draw it. It's nice being able to zoom in, you know. Okay, so this is joint C. And I've got this 2 kilonewtons coming downwards. Okay, and you know, I like to draw things in tension. You don't have to, but I do. Or at least I like to draw unknowns in tension. Okay, and so this is going to be BC, and this will be CD. Okay, so here's my joint. I'm going to go off on the side, and oh, well, this is the angle theta. Okay, and so X or Y, I think Y is simpler because it only has one unknown, which is CD. So we'll go sum of the forces into Y equals 0. And let's see here. So we've got negative 2 kilonewtons minus CD sine of theta. Oh, man. Equals 0. So, again, you know, that's your equation. This is the 3-point equation right here. And so then we're going to plug in, and we'll say negative 2 take gummit, give me that. Negative 2 kilonewtons minus CD sine 33.690 degrees equals 0. So CD equals, now CD's on an angle, so we're going to get something ugly here. We're going to get a negative 3.6056 kilonewtons. Okay, so CD is 3.6056 kilonewtons, and I drew it in tension. I got a negative, so it's going to be compression. Okay, so there's our answer for this one. We'll do the x direction. Sum of the forces in the x direction equals 0. Okay, negative BC minus CD cosine of that angle, like that. Again, there's your 3 points. Okay, so we're going to go negative. Is BC known? Do I know BC? I do know BC. That's interesting. Okay, so negative 3 kilonewtons minus CD, which we just solved for, right? Which is 3.6056 kilonewtons times the cosine of the angle, which is 33.690 degrees equals 0. And if I plug that into my calculator, I get 0 equals 0. Okay, so this, at least for me, this was a redundant equation. It may not have been redundant for you, right? Like if you had started at this joint, you would not have known BC or CD to start with, so you wouldn't have been able to. You wouldn't have been able to do this, right? So that's why the 3 points are here. Okay, but for me, it's a redundant equation. But for you, you may have gotten 3 points here. So if I was grading my own exam, I wouldn't have gotten 3 points here because it's a redundant equation. Okay, so, but anyway, so we're going to zoom over here, and we're going to look at joint D. D is, and you guys may or may not have noticed this, but I've been avoiding, well, after you didn't notice it, but when I worked this, I avoided D like the plague. I was like, I don't want to do D. You know, look at all these joints, right? We've got 1, 2, 3, 4 members. Now, there's no external forces, which is nice, but not only do I have 4 members, but 3 of them are at angles, and I got one of them straight up and down, and they're not even such that I can easily like turn the thing. I dislike this joint thoroughly, okay? Not as much as I dislike you guys, just kidding. Okay, maybe I'll put a little dotted line here to start this thing. But let's go ahead and let's see what we got here. So we got, you know, here's something going like this and something going like this. We got something going vertical. I mean, you know, it's like everything else. It sucks, but it's okay. It's not that bad, right? So when I get here, I know BD is let's see. So my unknowns, I'm going to draw. The thing is, I know a few of these, right? So I'm going to go ahead and draw this one going this way. I know that one's compressive. I know this one's compressive, so I'm going to draw that. I know AD is in tension, so I'm going to draw it this way. And this last one, DE, is my only unknown. Okay, and you actually could have gotten DE in another way. And we'll talk about that in a second. So you didn't even actually have to come here. So I guess there was a last way that you could have gotten this, but we'll talk about that in a second. So we'll go AD, BD, and CD. Okay, so let's go ahead and we'll go ahead and go theta. This is theta, that's theta. Okay, so we're going to do some forces in the X, some forces in the Y. Neither of these look particularly pretty. Let's see, in the X direction we've got 3, and in the Y direction we've got 4. So maybe we'll do X first. Sum of the forces in the X equals 0. Okay, so I've got negative AD cosine theta minus CD cosine theta plus DE cosine theta equals 0. Now the nice thing in this case, okay, again, this is my 3 points right here. But the nice thing in this case is all these cosine thetas, I can just divide them straight out like that. Okay, I don't even have to plug them in if I don't want to. So I end up with negative 2.7042 for AD, kilonewtons, minus CD, which is 3.6056 kilonewtons, and plus DE equals 0, so DE equals 6.3098 kilonewtons. Cool. Okay, I assumed it was in tension. So, wait, did I assume it was in tension? No, I drew it in compression. Oh, okay, so I drew it in compression, which is not normally my way, and it is in compression. So I screwed up there. At least I screwed up in that that's not normally how I would do it. And there's nothing wrong with doing it how I did it. It just, that's just how it works. Okay, so I have now solved for everything, but I'm going to go ahead and get, one more redundant equation. So, or this equation is going to be redundant. So the sum of the forces in the Y equals 0. And let's see here. So I've got, I guess I'll start at DE and kind of work my way around maybe. I don't know. Yeah, let's do that. So DE sine of theta plus AD sine of theta minus BD minus CD sine of theta. Okay, and that's kind of the nice thing when all of your angles are with respect to the x-axis, is that you can use the same angle and the same sine, right? Of course, it doesn't help us with BD, but such is life. Okay, so if we plug these numbers in, where's my, okay, so again, this was a potential plus 3 equation. Of course, it's, what's the word? It's redundant in my case. So DE is 6.3098 times the sine of 33.690, okay, plus AD, which is 2.7042 times the sine of 33.690, annoying, minus BD. BD was 3, if I remember correctly, minus CD, which is 3.6056 kilonewtons times the sine of 33.690 equals 0. And so this goes to 0 equals 0. So that's a redundant equation because we already knew everything, so it doesn't really matter. The last equation here that you could have done, and this would have been to get DE, is you could have gone down here and we could have done this joint down here. We could have done joint E, and joint E would have looked like this, right? And it would have had 6.3097 kilonewtons, and we would have had DE right here, and we would have solved and figured out that DE was compressive, right? We wouldn't have even done some in the X or the Y. We would have done some in the X prime direction, right? Because that would have been the easiest way to do it. Okay, so anyway, so once we've done all of that, well, that's interesting. I like it, but it's like really small. Anyway, so we go down here and we would just write all these numbers in here. So let's see here: tension, 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 compression, compression, compression. 6.31. We would round to 3 sig figs because nobody wants more than that. Okay, And that's it. Okay, and remember for this one, it was 3 points per equation that would solve for something. 1 point for correctly figuring out tension or compression based on your stuff, right? Because if you made a mistake early, it does propagate through these problems. And then 2 points for each what do they call them? Reactions. Okay, sorry, it's been a long week. Okay, so that's 30 right there. Okay, so again, remember, like, to cover any potential grading errors, I added 4 up here so that you could have, like, the 2 of you got over 100 on this, which was pretty cool. So, all right, yeah, that's right there. These are the two. These are the 2, right? And then a lot of these just really awesome. Just good job, guys. I'm really proud of you guys. So anyway, that's it. Have a good summer, and I did this in 1:15. So, and take care of yourselves. And if ever you guys need me, send me an email. Use my Gmail account. I'll see you guys later. All right, bye.